here I have several games. I'm going to very quickly write down, we are going to very quickly write down their strategies and then discuss what would be Nash equilibrium and subgame perfect Nash equilibrium of sum. So let's start with the first game. So I have two players. Player 1 has 3 actions A, B, C, and then player 2 observes the action of player 1, and then she chooses R or S. So this is a perfect information game. Question 2 is identical. They're the same game with the same payoffs. The only difference, which is a major difference obviously, is we have an information set, meaning the second player can't observe the first player's action unless it is A and the game is over in this case. And then I'm going to talk about question 3 and 4 later. So here, what is the strategies of player 1? You tell me. ABC, exactly. So I get rid of the brackets. Player 1 has only one info set or decision note, and therefore, and in this decision note there are 3 available actions, and hence he has 3 strategies. What about player 2? Does everybody agree with him? So there are 4 strategies, although he has 2 actions. Well, why is that? Well, because player 2 has 2 decision notes, and the strategy must assign action at each decision note. So the first one corresponds to his action in the first decision note, and the second action corresponds to his action in the second decision note. So RR means R here, RS means R here, S here, and so on. Very good. So these are the 4, these are the strategies of player 1 and 2. So if you want to write this game in the normal form, basically you're going to have 1, 2, 3, 4 columns and 1, 2, 3 rows for player 1. You just fill out the boxes and then find the Nash equilibrium. The Nash equilibrium of this game is identical to Nash equilibrium of this game. Okay? Sure. Thank you for this question because it really is important. So, again, the definition of a strategy says it's a function which maps decision nodes to an action available at that decision node. So here, this player 2, has 2 decision nodes, right? Let's call them N1. I don't want to call it N1 because 1 is the name of the player. Let's call it X and Y, okay? So X and Y, these are 2 decision nodes. Well, how many actions are there for this player? 2, right? X of R, and S. So therefore, when we say a strategy is a function maps decision nodes to an action, right? So we have from X to R, from Y, which one is X, which one is Y? This one is X, this one is Y. So from X to R, from Y to S. Is this a function? Exactly. First of all, if you don't remember the definition of a function, please go back to my videos for math review, okay? It's critical sometimes to understand very basic things like this. If you don't know the language, obviously you're going to miss it. All right, so clear the language first. So a function is basically maps each element in the domain. This is domain because this is the beginning of the function, and this is the range. So each element in the domain must be mapped to 1 and only 1 element in the range. All right? So we cannot leave any element here which is unmatched. all of them must be matched in the domain. In the range, we can have a bunch of elements which are not matched. Yeah, who cares? The domain, all the elements must be matched. Okay? So this is one function. And in fact, it corresponds to which of those strategies? R, S, this one. But is this the only function in this framework? No, there's another function. Let me erase this. Maps X to R and Y to R as well. So this is also a function. And it corresponds to what? RR. There's another function. It maps X to S, Y to S, which is this strategy. And then one more function, SR, which basically maps X to S and Y to R. Question is, can I define any other function in this world other than these four? No, I can't. I mean, try. Do you have any suggestion? Can I define any other function in this framework other than these four? No. Again, you can try. And if you have a guess, let me just say it's not a function other than these. So let me convince you. But do you have any suggestion? All right? So once again, a strategy is a function which maps each decision node to an action. All right? So here, you don't have to draw those diagrams, put the decision nodes here and the actions here, and then figure out all possible functions. There are easier ways of figuring this out. It's just how many decision nodes player 2 has? 2. So therefore, a strategy, I mean, you don't have to put comma. For example, here, I don't have any comma between the actions. All right? I don't have any brackets, as you wish. So if you're happier with this notation, so a strategy is going to be a tuple. This is corresponding to first decision node, or decision node X. And this is the second decision node, or decision node Y. So what are the available actions here, and what are the available actions here? Well, R and S, right? So how many combinations can I have for these two slots when I have two actions to fill in? 2 to the power 2, 4 available. So therefore, these are my old strategies. If I had, for example, RST, RST, how many strategies would I have? Well, again, I have two. The strategies of player 2 are going to be tuples, right? For first decision node, second decision node. But this time, there's going to be RST here, RST here. So it's like, for example, RR is one strategy, RS is another strategy, but RT is also a strategy, which wasn't here because T wasn't an available action before. You see what I mean? So the same thing, SR, SS, ST, and then TR, TS, TT. Is that it? Yes. So these are all the available strategies I can write for player 2, which makes sense because I have 3 available actions and 2 slots, so 2 to the power 2, 3 to the power 2, so 9 strategies. Okay, clear? All right. Well, what about the second question? What are the strategies for player 1 here? Again, strategy is a function which maps each information set, all right, into an action available at that info set. So here, there's no info set, there are nodes. So nodes and info sets are different things, but related. Info sets consist of decision nodes. But all the decision nodes in the info set will be treated as if one node. Okay? So here, how many, we're talking about player 1, right? So player 1 has still one decision node, so therefore his strategies are still A, B, and C. No change in here. What about player 2, though? How many info sets player 2 has? 1. So therefore, his strategy is not a tuple. All right? So it's just one sort of box to fill. Well, how many possible actions he has for this one box? 2. So 2 to the power 1, 2 strategies, which are R and S. So whenever I say strategy of player 2 is R, you should understand that player 2 is going to play R in both of these decision nodes because he can't distinguish whether he's here or here. So he's going to play S anyway. Okay? Here, however, he can distinguish these two decision nodes and say, my opponent played C. So I should play, for example, R here. And if my opponent plays B, I'm going to play S. So therefore, RS can be a valid strategy. Ask a very nice question. Do the player's strategies condition on the other player's strategy? And I said, in a simultaneous move game, this can't happen because you can't observe the other player's strategies or actions. So therefore, strategies are independent in a simultaneous move game. However, in the extensive form games, you can observe your opponent's strategy. So therefore, you can condition on your opponent's actions. Like here, I'm going to play R if you play C, and play S if you play B. I don't condition your action A because the game is going to be over and I don't have an option to make a move there. Here, however, I cannot condition upon your actions because I don't know if you're going to play or if you are playing C or B. I don't observe them. All right? So therefore, I just play R or S. Good? Okay. So if you want to find the Nash equilibrium of this game, well, then the normal form of this game has to be 3 rows, because player 1 has 3 strategies, and 2 columns, because player 2 has 2 strategies, and then find the Nash equilibrium. Okay? So here's one strategy profile. Okay? Player 1, A, and then player 2 plays RR. Is this strategy profile Nash equilibrium? So the easier question is, do you think player 1 here is best responding his opponent by playing A? What's going to be player 1's payoff if he plays A? Right? I mean, obvious. What would it be if he plays C? Good. Why 2? He's playing C now. Why is it 2? Look, what would be his payoff if he changed A with C? Fixing the second player's strategy, obviously, right? This is how we check Nash equilibrium. All of a sudden, you forget it. So if the other guy is going to play R here and R here, so let's put arrows. So we fix player 2. He's going to play R regardless. So if I play C, then I'm going to get 0. So clearly A is better than C. So C is not a best response. So your guess, good, but not correct. What about B, though? He's going to get 1, worse than A, 2. So you know what? Player 1 is in fact best responding by playing A. Conditional on his opponent is going to stick to this strategy R and R. But this is how we check Nash equilibrium, remember? Fix everybody else's strategy and see if player 1 or 2 or 3, you have to do it for each player, is best responding or not. So here A is a best response for player 1. Good. What about player 2? Is he best responding by playing RR? It doesn't matter because player 1 is playing A, so the game is over. it really doesn't matter whether you play R, you intend to play R as here. The game is going to be over if you fix the opponent's strategy A. So therefore, any strategy is a best response to A. Hence, in conclusion, both players are best responding to one another. Hence, this strategy is in fact a Nash equilibrium. So is it a Nash equilibrium? Yes, it is. Clear? Good. Well, let's kind of, the strategies are different here, but probably it's going to look something like this. Is a R Nash equilibrium here? The logic is the same, right? Is player 1 best responding by playing A? Well, fixing the other guy, player 2 is going to be playing R. Well, obviously A is going to bring him 2, C is going to bring him 0, B is going to bring him 1. All right, so therefore player 1 is best responding, player 2 is also best responding, right? Because the game will be over because the first guy is choosing A. So everybody is best responding. Hence, it is, yes, a Nash equilibrium. This is not a coincidence, obviously, because those strategies are kind of, related, right? It's just, I translate this strategy profile into this game. So they're outcome equivalents. So it makes sense that both of them are Nash equilibrium in these two games. Just to make sure that we are clear, perfectly crystal clear, let's check another, B, R, S. Is this Nash equilibrium? Again, start with a simpler question. Do you think player 1 is best responding player 2? Well, first off, always fix the other guy's strategy. It is R here, S here, right? So put the arrows, because it's easier to follow the arrows. So if he plays B, his payoff is going to be 3. Good. If he plays A, his payoff is going to be 2. So, you know what? B is better than A, therefore. What about if he plays C? If he plays C, however, he's going to get 0. So, you know what? C is also better than, B is also better than C. So, player 1 is in fact best responding. What about RS? Do you think it is a best response? Why? What would be a best response to B? Okay, you can't say just R, because R is not a strategy, first off. All right? Something like R something. RR would be a best response to B, you suggest. Let's see. So player 1 is playing B. Okay? So let's ignore those arrows, because now this time I'm fixing player 1. So he played B. So what you play here matters. What you play here doesn't matter. Okay? Here, do you want to end up with a payoff 1 or 2? Because you're player 2. So for that reason, I'm looking at the second numbers. Obviously, you want to get payoff 2. So therefore, you would want to play R instead of S here. So RS is not a best response because S here is not optimal action. Well, what is a best response to B? For example, RR is a best response, SR is a best response. But it has to be R here. So for that reason, player 2 is not best responding his opponent. Hence, this is not a Nash equilibrium. The subgame perfect Nash equilibrium we simply write as SPNE. Some textbooks call it SPE, subgame perfect equilibrium. I just like to put Nash there. So SPNE, we use the backward induction, meaning we start from the very last decision node. Not info set, decision node. All right, so here is one of them. Here is another one, right? The player 2 is moving. So this is one of the subgames. what is the optimal strategy here for player 2? It doesn't depend on player 1's actions, right? Because it's the final subgame. Well, clearly it's R because 4 gives him higher than 1. So let me put arrow here. Well, here in this subgame, what is the optimal strategy for player 2? Well, R again because 2 gives him higher payoff than 1. All right, so we say those guys are rational. So player 1, when he chooses his action, this is what he's going to be his thought process. He's going to say, if I play A, I'm going to end up 2. If I play B, I know my opponent will observe my choice and he will go for R, in which case I'm going to get 1. Worse than A. If I choose C, however, again my opponent will observe and he's going to go for R, which I will end up 0. So you know what? It's worse than A. So my best action here, given how my opponent will act in the second round, call it second round, I must choose A. So you know what? Just put arrows together in the following way. A is the first player's optimal action, and the second player's strategy must be RR. This is the only subgame perfect Nash equilibrium in this game. We're not talking about mixed strategies, at least for now. But this is the only pure strategy subgame perfect Nash equilibrium. Okay? Is this ARS? Is this SPNE? No. Because this strategy says the player is going to play R here and S here, but here playing S is not optimal. So you're going to say, look, player 1 is going to finish the game. It shouldn't matter for him whether he plays R or S. So why not? It is not. Why it is not an SPNE? Again, go back to the formal definition of SPNE. Subgame perfect Nash equilibrium is a strategy profile where strategies form Nash equilibrium at every subgame, meaning players must be best responding one another at every subgame of this game. So that means here, best responding, this is just player 2 choosing an action, right? It's not a best responding really, but it's choosing an optimal strategy, like payoff maximizing strategy. Is it R? Is it S? It is R. So therefore, he should always play an optimal strategy. SPNE, whether they will reach to this strategy, they will reach to this part of the game or not, is independent. Everybody should play their optimal strategies at every part of the game. So this is the concept of subgame perfect Nash equilibrium. All right? So it's stronger than Nash, meaning in any game, if you calculate Nash equilibrium strategies, probably there are going to be a bunch of strategy profiles that are Nash equilibrium, and there will be some subgame perfect Nash equilibrium strategy profiles, and it's always a subset of it, or maybe equal. For example, in this game, subgame perfect Nash equilibrium and the Nash equilibrium of this game are equivalent because this game doesn't have any proper subgame. But usually, like in this game, subgame perfect Nash equilibrium is going to be a strict subset of Nash equilibrium, meaning every SPNE is a Nash equilibrium, but there are some Nash equilibria which are not SPNE. Okay?